All right, good afternoon, everyone. And I'm going alphabetically, so sorry. Maybe next time I'll go reverse alphabetical. You're not always waiting for your exams to be graded. Okay. So now we're going to continue things, except rather than give you a system to analyze, we're going to give you, you might say, here's a system, synthesize it or get it done, right? But before we get into that, I just wanted to talk about different versions of the same thing. And pole zero format. All right, which recall, here's our imaginary and here's our real axis. That zeros would be done with a circle. It's where the transfer function equals 0. So that a 0 of -1, right, would look like, if I were to write it out in this format, 0 plus 1, because the actual 0 is -1, right? Same thing goes true for the poles, is that if I had a pole of, we'll call it -1/2 x, right? In equation format, we would have it like, we'd have it like that, because is what makes this go to 0, which makes the transfer function go to infinity. And you put an x there. First two of them, right, squared, you would just use that square. Poles and zeros times the zeros we had were actually at 0. Now, be complex, right? And you would just have something like s plus 5 plus 0.5 plus 0.5 minus, because complex values come in pairs. All right. So just because everything real before real. Now there's another that. Now here's the thing. This is h of s, right? And things in terms of h of s are called transfer functions. But this is called the pole zero format, and it's a form of transfer function. Then, if you read the Python code, there is, and those are written in terms of pol 2s plus 3. It, okay, I switched back to my normal speaker, but I am getting a message that my is but and I'll repeat myself. And Ryan, thank you for telling me where it is. But am I still coming in and out? All right. So all right. I'll just try to speak a little slower. So coming back to the pole zero, right? It's still a transfer function because it's actually where we can use algebra, right? A transfer function can look something like this, V out of S divided by V in of S, right? You can't do this in the time domain. You have to use convolution to get in, right? So to get out, you know, V out of T G of T convolved with H of T. Now, sure, if the Laplace transform of this, right, that gives you the transfer function, right? But transfer functions are a S domain. Now, in Python, there's another format called transfer function, which might be a bit confusing because in fact both formats are the S domain. But the format is you multiply everything out and you're just getting polynomials and you arrange them from, you know, the highest down to the lowest, and you have missing terms, and they can be positive and they can be negative, right? For a lot of what we're going to do for is we'll not pull zero so much as transfer function format, but it's really, you know, things are in polynomials. Okay. State space is in fact another form of the equation, but it's a time domain, all right? And so we're going to introduce something called a signal flow graph later, but you can have, right, goes into Hey, I'm still. Listen, I'm still experiencing. I'm getting notes that my internet is like weak today. All right, just give me a moment to make sure that everyone in the house is letting me teach. Okay. Yeah, I do have a cable modem. It's just lately it seems this time of day it slows down. Hope I've had people turn off whatever they were doing. All right. Alex, that's a great offer just to continue teaching rather than have to do a modem reset right in class. Yeah. Oh, that's wonderful to know. Excuse me?
Yes, sir.
Yeah, Alex, that's great. Just right now, is it good enough to continue? Because I really don't want to have to reset in the middle of class.
It's a lot better now, but it comes and goes, so give it a shot.
All right. Okay. Thanks. Anyway, you're going to have a signal flow graph where you have inputs and outputs, but you're actually using integrators and summers. Rather than the time domain, and that's a whole different. Really use it, but you probably would have you might have seen this in differential equations. Right. And if the recording is really bad, I will just redo it locally and post everything. Okay. So that's just some background, just to know that we're going to be in the we're going to leave time domain for some time, and we'll be in the frequency domain or the S plane so much that we might forget that time domain exists. We come back to time domain for the last part of the semester. So we have a thing called flow graphs. And we have inputs, right, which are a function of S, right? But many times I'll drop that out because it just takes too long to write. So in this example, it's actually a series configuration, and we have two what you might call mini transfer functions that we're going to make a larger transfer function for, right? One is a high pass, and the other one is a low pass. And because we're in the S plane, right, we can just multiply things together almost like op-amp circuits in series. So really equals the input times H1 times H2 right? And so we would get that configuration. So that's a good question, Javier. Does this make a bandpass? Well, let's see. So I've got 1, 0 at 0, and I have a pole at -1 and -10. And so I have things going on either at 0 or near 0, 1, and 10. All right. So when S or when omega is going to be a lot less than 10 and a lot less than 1, right? This will reduce to S times 10 to 1 times 10, right? And I'm getting a S term, which (20 dB per decade) and 0 dB at omega equals 1, right? Now let me take the other extreme where omega is a lot greater than 10, right? And so that transfer function is going to reduce to S times 10 S squared. We're left with 10 over S, and we're going to have a line going down at 20 dB per decade, right? Except it will equal 0 dB at 10, right? And then there'll be a spot in the middle where it's flat, right? And so this is a bandpass. But if I had really done this in a way where it didn't make a bandpass, it would make something really weird, okay? But in this case, now of course, right, we had a high and a low pass. So we can have our high pass. The gain was equal to 1. So we don't need any resistors, right? And then that goes right into our low pass. And then we just have to choose reasonable values of R and C, which we've done before. All right. Can anybody tell me though, why don't I just combine these? Why do I put the op-amp in between? You can answer out loud or in the chat.
Would you get oscillations in the system?
Wouldn't there be a voltage drop?
Okay, what I'm hearing are things about stability and voltage drops and things like that. And in fact, those are really good thoughts. Okay. And then there's, oh, even cleaning the signal as it enters the op-amp. But no, in fact, you can make a filter with these configurations. But what happens is H of S is, let's just call this C1, R1, R2, C2. In the op-amp, right, it's going to be S plus 1 over R1, C1, 1 over R2, C2. Okay. And so it's clean, it's easy. C1 is easy. C1 and R1 and R2 and C2 are easy to determine. You could determine R1s and C2s for this, but it is not equal to this equation. And you might call it, the resulting equation is what we call messy. But you might say, who cares? I'll just program it in Python, right? But what happens is that as it gets messy, right, this pole and this pole start to depend on every resistor and capacitor in the circuit. And that op-amp isolates it. the op-amp makes it so that we can easily synthesis, right? But sometimes you really have to get rid of an op-amp or you can't, and then you'll deal with it and you'll do that, all right? Emmanuel, I'm not quite sure if I understand your question. I mean, yep, we're assuming they're ideal. But even if there's a AV or gain bandwidth, right?
So it makes them more linear?
No, this is a linear time invariant system, just like this is a linear time invariant system. It just makes it so that I can take this transfer function and multiply it by this transfer function. But, you know, if I were to analyze this circuit, you know, let's just try to calculate a discharge time, right, from here. Well, the current can go that way, right? But it's got to go through this R2, but then that's being split, you know, from here and here. So this RC is affecting this RC. Same thing here is that the charge and discharge of this capacitor is affected by this. But because this op amp is ideal, right, the I going into it is 0. So really you can just, from analysis perspective, get rid of it. And you just have a classic RC circuit that you would have seen in 98 or differential equations, right? And this is an ideal, something that you might forget, right? But that the impedance of an ideal voltage source, right, equals 0. So that an ideal voltage source, right, won't affect the circuit. Now, of course, after doing the lab, you know that they tend to have 50 ohms, right? So that if I have 100 ohms here, and then there's a 100 ohm series resistance, it changes the time constant of the circuit, right? But as long as we keep this resistance much, much greater than 50 ohms, it behaves like an ideal circuit. Yeah, Vicente, I really like your summation. You do it so that each circuit is independent of each other, right? Which is like, you know, the phrase that you'll see like buffer, right? Buffer. Okay. Now, summation, right? Summation is a parallel process, and it's just like it says, it sums. Now, of course, you could have minus signs here as well, right? Summing doesn't just involve positive operations, all right? And so if we would get Right, we just follow it through. Ys equals Hs times H2 plus X of S times H1. Right, that's where this comes from. Right. Now, sure, I could, if I went too fast there, right, Y of S equals X of S times H1 plus X of S times H2, right? Gather the excess terms and move to the left-hand side. Now, while this is mathematically right, it's not really in a transfer function form that we need to use so that we're all speaking a common language, right? So you would have to multiply, you'd have to combine these. And then multiply everything out. Now, the important thing here to know, right, is you know what caused this circuit already, right? It was either a low pass in buffer configuration or high pass. In buffer configuration, right? But I think it's pretty easy to tell, right, that there's no imaginary number, there's no complex root involved from here, right? No matter how you derive it, you will just come out with a first order system, right? If everything is ideal. And we're going to ultimately spend a lot of time designing filters that have a complex poles. All right. Now the why of it comes later, but the thing is that if I start with real poles and I sum them together, right? Even when I multiply these together, well, I'm already in pole zero format and they're not complex. So just multiplying real poles or real zeros times each other does not make complex poles. And so when you really have the same energy storage element, right, capacitors or inductors, you can't get complex poles. All right. Now, just, quick review. We have a mass swinging back and forth. And you probably remember you can have over, under, critically damped, and that there can definitely be complex poles in this system. But remember, there's two ways the energy is being stored, right? Kinetic energy and potential energy, right? So that's what allows you to get complex poles. If I have a mass, right, and a spring and a damper, right, that spring is a different kind of energy storage element than mass. So that allows you to get complex poles. I'm going to show you something, a feed technique that allows you to get complex poles even if you're just using resistors and capacitors. And that's the feedback method. All right. And the filter method that we're using will actually use series, parallel, and then the feedback method. All right. Now, it might not seem at first, but the RLC circuit is a summing technique of the series. And let's just remind ourselves, right? ZR equals R, CL, SL, ZC. All right. And notice the position of S in these two energy storage elements, right? They're the inverse of each other. So, yep, we can get complex poles. All right. So if I look at this from a mesh standpoint, right? Right, I have all my I is all the same, right? And that minus V in. Oop. Right? They all sum to 0. Or we could just write it this way. Notice it doesn't matter the order they're in. Vn will sum to all three of these voltages. And so in fact, that's why this can be used as a summing technique, even though it doesn't have an OPAMP, right? Now, there are two ways to find the transfer function, right? One would be, and let's say it's a VC, right? VC over VN, right, would be the voltage division, right? Right, I could find it that way, right? I could, as I'm using, mesh analysis, right? I have I times R plus I SL plus I S over C, right? I solve for I, right? Then multiply by ZC to get my V out or my VC, and go from there. But really, in this case, I would just use voltage division, right? So we have 1 over SC, R plus SL, oops. All right. Now, this is a mathematically valid equation. And for instance, if I were to ask you, what is the transfer function of this on a MyOpen math exam, it would actually mark it correct. But it's not really in the transfer function format, And it really has to be in that format. Just one, because when it's in that format, there's things that you can just tell about the system for just looking at it. Also, there's things, I think Kevin mentioned stability, and somebody also mentioned oscillations that are a lot easier to tell what's going on when everything is in a polynomial, descending polynomial format. All right. So you have to be able to get this in the right form. Also, you will not find an inverse Laplace transform of this, right? And yeah, I guess as I know that I'm looking for a numerator in terms of S plus something S plus some constant, and then a denominator something like that, right? I know where I'm headed because I've done this a lot. It can be different. It's all a bit brand new. All right. But so right now, this S term here is not in descending polynomial format, and S to the -1 doesn't count. All right. So in fact, I'm going to multiply through by S. And slightly rearrange the terms. All right. So now it is in descending polynomial format. However, you want this first polynomial to be scaled by 1. All right. So I pull out the L, and I'm just going to put it up front. So now I have S squared, R divided by L plus S, plus LC. Now this is actually equal to where we just kind of call things, not worrying that they're circuit parameters anymore. All right. All right. We're going to talk about this more later, but this is our omega naught, which is not necessarily the breakpoint where it was before, but it could be very close to the breakpoint, or it's in between two breakpoints. All right. And this is a damping factor, which kind of controls what somebody had been talking about earlier, which is oscillations. All right. Zeta Y. Okay, let me try to do that a little better. Okay, it's a zeta and it's damping factor. Okay, yeah. All right. Now, oh, is there a question? Okay. Now, the thing is how to design a filter with this is choose L, right? Then calculate C.
You're missing an S on the second term, right? In the denominator.
Thank you. Yeah, there's got to be an S there. Okay. So inductors are harder to find or harder to get the value you want. They can be large and actually expensive parts. So in fact, you choose the inductor first, right? And then you calculate the C based on this equation, right? And yeah, is it a capacitance that even exists? You have to kind of keep choosing back and forth until you get one, right? Then once you have the C, then you calculate the R and then check, right? Is R greater than 2 kilo ohms? If it is, then that's probably a reasonable design, right? And C, reasonable is can you buy it, right? So what I have here is a list of inductances that you can buy from Anchor Electronics, right? And I believe everything is pre-scaled for microhenries, right? So then it calculates a capacitance value and rounds it, and then calculates the R. And then basically if R is greater than 2000, then it'll spit back the what you want, right? This you'll probably recognize as me printing out things so that I don't have to write them out in LT Spice, and then it makes a nice little plot. Okay. So I wanted a 50 kilohertz cutoff low pass frequency. It gave me an R, L, and a C, right? And then these other things are, I wanted the Bode plots to go several orders of magnitude above and below. So it actually calculates that out. And then if I were doing a filter that we're going to go over later, these are these constants that you would use, all right? And so there's the Bode plot. And then what this is the impedance. And interestingly enough, at omega naught, right? And in this case, omega naught is at minus 3 dB. That's because this kind of filter is designed to do that, right? So at omega naught, the impedance is minimized. Now the impedance is not 60 ohms, it's all in dB so that you can see it plot. So to find the true, what you'll find is that the minimum resistance or impedance is 2.48 kilo ohms. All right, that's how you would do that. Now, another way to use that So if you looked at this filter and you wanted to synthesize it, you'd say, hey, there's a positive sign here. You know what I can do? I can add these two together. Right? There's the denominator, right? So I can have an RLC circuit that creates this. I can have an RLC circuit that creates this, and then just sum them. Now I don't want to draw out the whole circuit. So let's just say H1, H2, and then I sum. Right. And the summers, right? We know how to create those already. Those are op amps. So zeta is a damping coefficient. And if you remember over, under, and critically damped, like a zeta equals 1 is critically damped. Zeta less than 1 is under damped. There's complex roots. Zeta greater than 1, 2 different roots. Okay. Now, to show you the oscillations, I'd rather wait for another time. Okay, Sam? Is that enough? Okay. Thanks, Sam. Now, the thing is that's, you know, it's an RLC circuit, and an op amp. Well, the note, if you recall, we had VR plus VL plus VC equaling VN. And in fact, VC, we already showed, was the low pass. What I didn't really show was that VL is the high pass, right? And all I'd have to do is switch those terms. And that would become a high pass filter. But notice how everything is summing up. I really just want to sum these two together. The denominator is already the same. So why not call this V out, right? And I can draw it a little bit differently. There's my low added to my high, right? Because VC is my low, VL is my high. And now I've got, now sure, you're more than likely going to need a buffer, but you were able to get a notch, right, just by rearranging these. And even in the, and I don't really have to have these in this order. I could still have the inductor and the capacitor in the same order, right? VR, that would be the band. Now, I know sometimes I can be a little bit confusing when I start talking about like a practical design, and we talked about, you know, resistors that made sense. And I think we can all see though that, you know, resistors above 2K make it so that it doesn't matter if your signal supply source has a series resistance of 50 ohms, right? And we just know that some L's and C's are fabricated and some are not. All right. but a lot of it can come with like, so for this, and what I'm saying is sometimes you don't really know something's going to work ahead of time. All right. And so it turns out, like, what if I want to make an RLC circuit at 10 kilohertz? Right. Okay. I put in a made up value here the other day. At anchor, 5.6 millihenries is pretty much what you can do. So now I didn't do a fancy software to say, to check for this condition, but my program won't run because for the inductor values created, I can't create a resistance over 2K, right? And then I have to go back and rethink my design. Okay, feedback. So everything so far, right? We have X of S, we go through some system, and we get Y of S. And everything just goes in one direction, right? Either series, right? Or parallel. But we're going to talk about signals that actually take the output and feed them back into the system. And this is the feedback technique. Now let's talk about let's just redraw the circuit of an integrator, non-inverting. All right, so it can be shown that HS of this system is just 1 over S. So that's just an integrator, right? We also have this circuit, which is an inverting integrator. And what's going to happen is we're actually going to use this one and we just keep track of the minus sign, right? They're always using a non-inverting integrator, right? But this takes more parts than this. This is a lot simpler to use. So this is the structure for the kinds of filters that we're going to be using. All right. So when I'm using this 1 over S, it's really a minus 1 over our CS, right? But that's when I'm starting to build the circuit. So let's just make a simple flow graph. So this is a signal, simple signal flow graph. H1 it's just 1 over S, all right? Sure, it's really this circuit, so it's going to be minus, but for right now, we're not going to worry about it. Because if this is minus, oh, all I have to do is add it on the summer and it'll take care of itself. But that is another day. Let's just do this. So we take X of S, it comes into the summer, keeps going, gets multiplied by the transfer function, and then is equal to V out. All right, so V out equals X of S times H1. All right, but there's this feedback loop that we hadn't had before. So what else is V out equal to? Well, V out is also equal to minus, so V out, because they have V out multiplied by -1 multiplied by H1, right? And that's what so this V out is here. What does it equal? It equals itself times -1 times that transfer function. So now let's collect the V outs. I'm just going to scroll this down a little bit so that we can all see. Right. So now we solve for the transfer function. Now, this can give people a little bit of trouble. Notice how we're subtracting the output. That's negative feedback, right? But notice how it's positive in the transfer equation. Well, that's because when it's subtracted here and you bring everything on to the left-hand side, it turns positive, right? So yeah, the negative feedback actually has positive coefficients in this equation. All right. Now, in this case, H1 equaled 1 over S. So that's 1 over S times 1 times 1, S times 1, S times 1 over S, and we have a low pass filter, right? But the circuit is made up of out of a summer and an integrator, okay? Now this is actually the same graph, except before I was taking V out here Now I'm taking it out here. So I just redrew it differently, but really, right? I'm just taking it out here. All right, so let's read. So what does V out equal? Right, V out just equals X, right? But V out also equals, right? V out times H. Oh, but it was minus. Okay. Collect the V outs. Find the transfer function. Okay. Now this function here, it is mathematically correct, but it is not in the right form. So to do that, we got to put it in the right form, meaning things have to be in descending polynomial order here, and things have to be in descending polynomial order on the denominator. Nothing that looks like this. And so we get S plus 1. So here's the thing, that's high pass. So there's a high pass node, and there's the low pass node. So a lot of you might have been getting some feedback on your exam that your reasoning on part 5, right? Why is something a high or a low pass filter, right? Yeah, if you it is true. A is a low pass filter because it looks like a low pass filter. It's a true statement, but it doesn't really tell me, right, in your own words, what that really means, right? So things to explain that are, right, you know, things like attenuates high frequencies, right? Reduces high frequencies. Signals being passed through at higher frequencies are smaller than lower frequencies at lower frequencies, right? And the opposite would be for the high pass, right? It attenuates lower frequencies and allows higher frequencies to go through, right? Or higher frequencies will be kind of a higher magnitude than lower frequencies, right? You have to, I'm looking for you to be able to explain, you know, what it is about that curve that really makes it what it is. Now, these words that I'm saying are actually in previous exam solutions, okay? And I did say them in class, but maybe I went a little bit too fast, right? But So that's what makes a high and a low pass, right? And then what, as a result of attenuating high and passing low, right? Well, if I have a step response, right? Well, it's DC here and it's DC here. So a low pass filter will start off at 0 and then end up at some DC value, which could be negative, right? And then the curve looks like something like this because it's rounding these edges, right? Because those edges are of a high frequency, right? The step is 1 over S. The magnitude of that is 1 over omega. So maybe the frequencies fall off as omega goes up, but still there's a lot of frequencies because you start and end with an infinite slope. All right. Now, what is the consequence of high pass? Well, it's kind of blocking DC, right? So if this is my step, it's actually blocking 0 and blocking high, but because of the nature of the circuits we use, it really will start at 0 and end at 0, right? And it passes high frequencies a lot, very well, which is right at that step. So it goes up, but of course, in many of the circuits there that we did, they're exponential decay, and so it comes down like this, right? Now, yeah, there's questions, right? High pass filters tend to have a delta function and something in the opposite direction that starts at 0, goes to something and comes back to 0, right? Now you could have an inverting high pass filter, and now we're talking about time, right? So a high pass filter has to have the original thing, and then it has kind of a low pass response built into it. But with the two of them, you get edge detection and you are blocking DC, right? Where here, right, that is the impulse response of an RC circuit, right? But that could be approximated like this, right? H of t starts at 0, goes to something, comes back to 0, right? That's like a low pass shape, which will round things out, right? And if I'm convolving this shape, let's convolve that shape, right? It'll start going in, it'll start to increase, the overlapped area will increase, but then at some point, the overlap doesn't increase, and so it flattens out, all right? That's the kind of thing that I'm looking for, right? Then the next part is, well, there were too low and too high, right? Well, one should, right, you can get tau from the cutoff frequency, and I think we're running out of time. But we can, if you're having problems with that, we can have individual conversations. But I just thought to mention that. All right. But that's all I have. No, Sam, I'm not. I've got 30 left. Okay. Well, if that's it, go enjoy 112. Have a good day.